Hi there. Our talk is titled Going Beyond the Point Neuron, Active Dendrites and Sparse Representations for Continual Learning by Karan Grewal, Jeremy Forrest, Ben Cohen, and Subutai Ahmad. This is work done at NUMENTA, a research lab at the intersection of neuroscience and computer science with a dual mission. The first is to reverse engineer the neocortex and develop a framework of how it works. The second is to apply neocortical theory to machine intelligence and create truly intelligent machines. One aspect of human intelligence that interests us is continual learning, which is the ability to learn tasks or concepts in sequence without losing previously acquired knowledge. Continual learning is crucial to intelligence because an autonomous agent should be versatile and able to do more than one thing. For instance, early in life, children learn to ride bicycles. Years later, they learn to drive cars, but don't forget how to ride bikes as a consequence. It turns out that artificial neural networks are not suited for continual learning. One reason for this is that they use a point neuron as their basic computational unit, which abstracts many details of real neurons into a simple linear weighted sum, followed by a nonlinear activation function. Consequently, the artificial neural network, abbreviated as ANN, comprising these neurons, modifies approximately 50% of its parameters when learning just a single example. These changing parameters correspond to the green weights in the diagram on the right. This is a terrible outcome from a continual learning perspective, as most knowledge is easily erased over time, and hence leads to a phenomenon known as catastrophic forgetting. We augmented ANNs with properties of real neurons that we believe help with continual learning. First, a pyramidal neuron is much more complex than the point neuron and has many dendrites which affect the neuron's output in different ways. Proximal dendrites, located close to the cell body, receive input that can directly cause the cell to fire. However, most dendrites are distal, which means they are far away from the cell body, and instead of causing an action potential, they heighten the chance that the neuron will fire. These segments are thus referred to as active dendrites. In our modified neuron model, we incorporated active dendrites by adding multiple dendritic segments that act as independent pattern recognizers and modulate the output of the neuron. These segments receive a separate input than the feed-forward input, which we call a context vector. Second, neural firing in the brain is extremely sparse due to local inhibition, with less than 1% of neurons emitting an action potential at any given time. This video tracks neural activity in the neocortex of a mouse as it performs a certain task. Notice the sparsity level. We use the k-winner-take-all function as our choice of nonlinear activation to implement local inhibition. K-winner-take-all works by selecting the top k neurons with the highest activation value and dropping all others to 0. With a small value of k, it forces sparse representations in each layer of a network. Putting active dendrites and sparse representations together, we arrive at our model, the active dendrites network. Our model receives a feed-forward input and an additional context vector. Note that we also use sparse feed-forward weights, which are 50% sparse. What do we hope to accomplish with active dendrites and sparse representations? Active dendrites can decide how and when to modulate the firing of a neuron by either encouraging it to fire or turning it off entirely. Coupled together with sparse representations, different subnetworks can emerge at different times. Note that training one particular subnetwork won't cause the weights of another to be modified, as backpropagation doesn't affect the weights of neurons whose activation value is 0. This is promising from a continual learning perspective, as we can train different subnetworks on different tasks without any interference. Moving on to our results now, we tested the active dendrites network on permutedMNIST, a benchmark continual learning dataset. In this dataset, each task consists of classifying images of handwritten digits from 0 to 9. However, the pixels of all images are permuted according to a single pixel-wise permutation. The target labels remain unaffected for all tasks. In each task, roughly 50,000 images are used for training and about 10,000 images are set aside for testing. There are many possible ways to compute a context vector that dendritic segments receive. However, we used a simple method. MNIST images can be thought of as high-dimensional vectors according to their pixel values. These images are likely to cluster differently based on which permutation of the pixel is applied. When training on a specific task, we found the average vector across all training images for that task and used that as the context vector. We trained an active dendrites network on up to 100 permutedMNIST tasks in sequence, and it achieved more than 80% test accuracy across all tasks. We compared our results to synaptic intelligence, abbreviated as SI, a popular method to mitigate catastrophic forgetting in neural networks, and our results were competitive. Furthermore, we found that SI is complementary to our approach, since combining the two yields over 90% test accuracy when learning 100 permutedMNIST tasks in sequence. Our results are encouraging, but what are active dendrites really doing? This diagram shows the activation frequency of neurons in a hidden layer of our network grouped according to each of the 10 tasks they were trained on. As can be seen, different neurons become active for different tasks, which means that representations mostly don't interfere with each other. This next figure illustrates how different dendritic segments respond to different context vectors. The top row of diagrams shows the responses of dendritic segments to context vectors for different tasks at initialization. These are random. The bottom row of diagrams shows the same responses after training. Notice how each neuron has a few segments that respond strongly to different context vectors. These neurons are being upmodulated for certain tasks to pass through the K-winner-take-all function. One important question in computational neuroscience is whether dendrites add any special functionality, or if they can just be replaced with deeper ANNs. We compared our active dendrites network to standard multi-layer perceptrons with 3 and 10 layers on 10 and 100 permutedMNIST tasks. When learning 100 permutedMNIST tasks in sequence, a multi-layer perceptron can't achieve better than 50% test accuracy, whereas the active dendrites network achieves above 80% test accuracy. Although previous studies have found dendrites add no computational value beyond capacity, this large accuracy margin suggests that continual learning settings are more complex environments in which properties of active dendrites cannot be replaced with deeper neural networks. In summary, we provided the following 3 contributions. First, we augmented ANNs with properties of active dendrites. Second, we showed that active dendrites networks mitigate catastrophic forgetting and perform better than standard ANNs in continual learning settings. Dendrites, therefore, cannot always be substituted for more layers. Third, we showed active dendrites invoke mostly non-overlapping subnetworks of neurons that each specialize in learning different tasks. These subnetworks emerge naturally as we don't explicitly encourage them. Our preprint is available online and contains details of our model, methodology, and results. If you have any questions, please feel free to reach out. Thanks for listening.